Hello everyone, welcome to a new lecture in the series of AI using Python. In this lecture, we will be focusing on convolutional neural network or CNN. Convolutional neural network or CNN is a deep neural network which comes under the class of deep learning algorithms. In general, a CNN consists of different kind of layers such as convolutional layers, subsampling or pooling layers, and layers of feed-forward neural network. So here the convolution layers are the key element of a CNN which distinguish CNN from other kind of neural networks. In general, the convolution and pooling layers are used for dimensionality reduction and feature extraction. And the features extracted with the convolutional and pooling layers then will be used as inputs to the feed-forward NN, which predicts the output. And the convolution layers are used for representing temporal or spatial relationships in the data, which makes CNNs suitable for processing data such as images data or time series data, etc. Let xk and hk are two finite sequences. Then the convolution of x and h can be defined as in this equation, where we will be flipping one sequence and shifting it along the other sequence and multiplying corresponding elements for obtaining the output. Here, xk contains n number of samples, hk contains m number of samples. We can perform convolution either by flipping hk and sliding it across each sample of xk, or by flipping xk and sliding it across hk. This equation indicates that the convolution operation is performed by flipping one vector and sliding it along the other vector and perform an element by element multiplication. Here, we discussed convolution with the data represented as vectors, which is normally in the case of time series data. Similarly, we can perform convolution of matrices and tensors as well. And in most of the CNN case, we will be performing convolution with the matrix data. Especially in the case of image processing applications, we will be using convolution of matrices. In CNN, the convolution filters, which can be represented using a matrix or vector, will slide along the input variables to extract the key features in the data. Generally, we can represent convolution as a matrix multiplication, and the elements of convolution vector can be considered as parameters to be trained. And in convolution layers, the convolution operation is normally followed by an activation function such as ReLU, which is then followed by pooling and sampling layers as well. And here the convolution and pooling operation is represented by a function fc, and the feed-forward network can be represented using a function fnn. Theta c represent all the parameters in the convolutional layers, and theta nn represent the parameters in the feed-forward layers. And CNNs are trained for optimizing the convolution filter parameters along with the weights and biases of the feed-forward networks. The training data for CNN consists of the inputs, which contains n number of observations such as x1, x2, xn, where each xk contains small n number of variables. And also the output observations, which are denoted by y1, y2 to yn, where each output vector contains small p number of variables. Then the optimization problem for CNN is to find the parameters theta c and theta nn, which minimizes the prediction error over the training data. And CNNs are used for various applications such as image classification, image and video recognition, recommendation systems, natural language processing or NLP, time series analysis, etc. In this lecture, we will be considering this first application, and we illustrate CNN using the MNIST dataset. First, we will be loading all the libraries. Next, we will be loading the MNIST dataset using mnist.load command, which download the dataset from this site. Then we can normalize the input data between 0 and 1 for training the CNN. We define the CNN model using this thing, in which we have convolution layers and pooling layers of size this, another convolution layers with this size and activation function as ReLU, and another pooling layer, which is then followed by a feed forward NN with activation softmax. These parameters we can change, and the number of these convolution layers and pooling layers can also be increased based on the application. Now we can compile the model where we will be using Adam as the optimizer. and cross entropy as the loss function. Once the model is compiled, we can train the model, where we will be using the model.fit command for training the model. And here we will be considering 5 number of epochs and train the model using the input and output data XTR and YTR. Since the CNN contains large number of parameters, training will takes more time compared to normal for a neural network. Once the model is trained, we can evaluate the performance of the model by using model.evaluate function, which will give the test accuracy as 99% and the loss as 0.03. Now we can also predict the output for a few images and plot it. And here we plotted the predicted output for 10 images. So for this first one, the actual value was 7 and is predicted as 7. And similarly for image 2, actual value was 2, predicted also 2. And here we can see that for all the 10 images, the predicted value is correct, which means that the model is pretty accurate. In the next lecture, we will be discussing recurrent neural network, which is also another deep learning model. That leads to the end of this lecture. Thanks for watching.